In 2009, British physicist Stephen Hawking staged a strange and playful experiment. He hosted a party for time travelers with balloons, champagne, and an open invitation. But there was one twist. Hawking only sent the invitations after the party was over. He waited, but no one came to his time traveler's party. For Hawking, this was not just a clever stunt, but a demonstration. It showed that backward time travel might be impossible in reality. After all, if time travelers existed, why didn't any show up? Yet Hawking and many other scientists did not dismiss the idea entirely. They argued that if time travel were possible, it would likely be limited. You could never travel to a moment before your time machine's invention. The past might be closed to us forever, but the future is different. In a sense, we are all time travelers moving through time. At this very moment, you and I are moving from the present into the future. We march forward at a steady pace of 1 second per second. But just as rivers do not flow evenly, time itself can change. The flow of time can vary depending on where you are and how you move. Modern science reveals that time can stretch, warp, and bend in several ways. These methods don't just exist in theory, but have been tested and measured. Today, we'll explore the 5 main scientific approaches to time travel into the future. The first and most practical way to journey into the future is through speed. Einstein's special theory of relativity showed that faster travel slows time for you. This isn't speculation, but has been tested and proven through experiments. In one famous experiment, scientists used 2 atomic clocks for comparison. One clock stayed on Earth, while the other flew aboard a jet aircraft. When the jet landed, the flying clock was ticking slightly behind the stationary one. At everyday speeds, the time difference is tiny and almost invisible. But at extreme velocities near light speed, the effect becomes dramatic. A person on such a spaceship would experience time passing at half the rate. For every year that traveler aged, more than 2 years would pass on Earth. Push even closer to light speed, and time dilation grows extremely powerful. This could allow astronauts to leap forward into Earth's distant future. Nature itself gives us proof through muons created in Earth's upper atmosphere. Muons typically decay in just 2.2 microseconds under normal conditions. But when moving close to light speed, they last 10 times longer. Their lifespan is extended by time dilation itself through velocity. The universe already provides a path to the future through speed. The second method comes not from speed, but from gravity's influence. Einstein's general theory of relativity revealed that gravity affects time flow. The stronger the gravitational field you experience, the slower time flows. Gravity bends not just space, but time itself according to relativity. This gravitational time dilation effect has also been measured and confirmed. In 2010, researchers placed 2 atomic clocks just 303 centimeters apart. The lower clock, closer to Earth's gravity, ticked more slowly than the higher one. On Earth, the gravitational time difference is tiny and subtle, but near a black hole, the time difference becomes absolutely monumental. At the edge of a black hole's event horizon, time almost freezes completely. Hollywood captured this idea in the film Interstellar, with dramatic time dilation. On a planet orbiting close to a black hole, time passed differently. 1 hour passed locally, while 7 years raced by on Earth. Physicist Kip Thorne admitted such extremes may not exist in our universe. But the principle of gravitational time dilation is scientifically sound and real. In fact, our everyday technology depends on correcting for time dilation effects. GPS satellites orbiting Earth experience both velocity and gravitational time shifts. Without constant adjustments, your phone's map app would be off by kilometers. The lesson is clear. Gravity is not just a force pulling you down. Gravity is a powerful sculptor of time itself throughout the universe. Not all time travel requires warping space-time through physics alone. Another possibility is slowing ourselves through suspended animation techniques. Across nature, suspended animation already exists in various biological forms. Bacterial spores can survive for millions of years in dormant states. They wait for conditions to improve before reawakening to active life. Mammals like bears and squirrels enter hibernation during harsh winter months. They lower their metabolism dramatically to survive without food for months. Could humans achieve similar suspended animation states through scientific means? In 2005, researchers exposed mice to tiny doses of hydrogen sulfide gas. Their body temperature dropped to 13 degrees Celsius during the experiment. Their metabolism slowed by a factor of 10 compared to normal rates. After 6 hours in the state, the mice were revived with no harm. Larger animals have resisted similar attempts at induced suspended animation. Yet human clinical trials are already testing hypothermic suspended animation techniques. Doctors replace a patient's blood with cold saline to preserve them during trauma. While we may not yet sleep through centuries, progress is being made. Suspended animation may allow us to skip ahead by slowing our biology. The fourth method is among the most exotic: wormholes through space-time. Einstein's equations allow for shortcuts through the fabric of space-time. These tunnels could connect distant regions of the universe or different times. Some scientists speculated that tiny wormholes may constantly flicker in existence. They might appear and disappear at the quantum scale of reality. The challenge is capturing one and expanding it to human size. The energy required would be beyond anything we can imagine today. Worse, stabilizing a wormhole might demand negative energy not known to exist. Still, the idea fascinates physicists and storytellers across many disciplines. Wormholes may remain only a theoretical possibility for the foreseeable future, but they stand as a reminder of how strange the universe might be. The fifth idea comes from American physicist Ronald Mallett's rotating light theory. He proposed using rotating beams of light to twist spacetime itself. Mallett suggested circulating lasers could create a strong gravitational effect. This could bend time into a loop, allowing potential time travel. In theory, this might allow particles and perhaps people to travel through time. Since 2000, he has sought funding for experiments with neutron beams. His theories remain controversial, with many physicists skeptical of assumptions. Yet his work embodies the spirit of exploration and daring imagination. From Hawking's empty party to experiments with atomic clocks and beyond, humanity's search for time travel spans physics, biology, and pure imagination. What have we learned through all these scientific explorations of time? Traveling into the future is not only possible but already happens. Speed, gravity, and biology all show us paths forward through time. Traveling into the past remains elusive and perhaps fundamentally impossible. No traveler has arrived from tomorrow to prove otherwise through evidence. And maybe that is for the best if the past is fixed and safe. History remains protected, while the future is still unwritten and open. As we push science's boundaries, one truth remains constant through time. We are all travelers on the greatest journey through time itself. Subscribe, like, and share to see more such interesting videos from Time Flipped.